So the topic is work and energy. My experience with this has always been different than what I expect from you guys. So let me start out by just a couple quick questions. How many of you have a vague recollection of how energy is discussed in chemistry? Say again? Okay, well, what would you say? How is energy discussed in chemistry? All right, that's fine. Every year I ask the question, I get a mixture of results. Let's start with what I think is the right place to begin. How many of you know what that is? Like, could define it? Jack, what do you got? What do you know about it? It's in food. Thanks, Jack. Way to go. Yes, sir.
It's like the amount of energy needed to boil a milliliter of water.
All right. No, but we're getting closer. Yes, sir? All right, let's start with that. It is a unit of energy. Excellent. So at least we can start there. So and Jack will help us out in saying that there's a difference between these two words, one with a lowercase c, one with an uppercase c. So this one has to do with food, perhaps, and is 1,000 little calories. All right, so we did get some idea that this might have something to do with water, and it does, but not boil. It's the amount of energy required to raise 1 gram of water 1 degree Celsius. That's how a calorie is defined. The amount of energy required to raise 1 gram of water 1 degree Celsius. And when we talk about that, specifically we talk about heat energy when we're dealing with chemistry. This is heat energy. Usually in chemistry, if you're not dealing with some kind of chemical relationship, we talk about the transfer of energy using one of 3 methods. Do you guys remember what those are? No. If we can get one of them, you can usually get the other 2. You just need the context for at least one of them. Nobody?
Can you repeat the question?
How does energy transferred in chemistry? Yes, sir? No, I mean, that's always true, but that's not exactly what I'm looking for here. Yes, sir?
Conduction.
There we go. Conduction. Contact. Convection. Mixing. Or fluid. And the last one? Yes, sir? Radiation. And now you can say these are the spontaneous flows of energy that go from areas of hot to areas of cold. So it is true that energy will spontaneously flow using one of these 3 methods from an area that has more energy to an area that has less energy. And all together in chemistry, how do we measure energy? There's one way. No. That's how energy was measured in chemistry. That's right. So if we talk about energy in chemistry, that's really what you have. Now there's probably stuff with, you trying to measure the energy of a reaction and how much energy is released. You might have even had words like endothermic and exothermic. Those sound familiar too? All right, so when we talk about energy in chemistry, generally this is the conversation that's had. I bring it up because energy in physics is not dissimilar to this. Energy is energy, regardless of the type in which you're looking at. The difference is that in physics, we're talking about mechanical energy, which means we're related directly to movement. We don't see mechanical energy in chemistry because we can't really see or easily rationalize the motion of the particles. But temperature is a direct measurement of the motion of the particles. You should have learned that when you learned about the Kelvin scale. That the reason why the Kelvin scale even exists is because when you're measuring in Kelvin, you're measuring directly the amount of motion the particles have. So 0 Kelvin relates to no movement in the particles at all. So this was a hope that you had some idea of what we do in chemistry, but clearly not so much. So we define energy by defining a property called work. And this is the property that we will use to define energy. Now, I don't want to belabor this very much because your understanding of this is not necessary. But all forms of energy in all disciplines are the same. When you're measuring energy, you're measuring the same thing. And work is the actual method by which an object's energy is changed. And I'll say that again because I want that in your notes. That's the definition I want you to have. Work is the actual method by which an object's energy is changed. Whether we're talking about chemistry or biology or anything else, work is the actual method by which an object's energy is changed. And that method involves the use of a force. So in all forms of energy exchange, a force is used to transfer energy. Now for chemistry, we can't see that because it's happening at the molecular level. But in physics, we can. And we can apply forces to objects, and when we do so, we are transferring energy from one object to another. The basic definition of work, and when I say basic, I mean how we will define it as an equation, is it's not complicated, but it has 3 parts. And first, I want you to know that work is a physical quantity. I will not write out W equals. I will write out the word work because we have W for weight already. And it becomes pretty, I feel pretty confusing if we're not careful here. So for a long time in this unit, I will simply write out the word work. But work is a scalar quantity. That's the first thing I want you to know. It is something that is done. And after it's done, energy has been transferred. So we talk about work. It's a scalar quantity. It is something that is done. We say you do work on an object, or an object does work on something. And after it's done, energy has been transferred. Let me throw in something here. Newton's third law. Because work involves a force, anytime something does work, one thing gains energy, something else in the universe loses energy. So for all applications of work, wherever something's energy increases, someplace else in the universe, energy had to decrease. And that's due to Newton's third law. And we're going to see that too. So, last, this involves a force. Over a displacement. For work to be done, an object's position has to change. For work to be done, an object's position has to change. So, work. It is the product of 2 vectors. Didn't leave myself enough space there. This is how we calculate work. It involves three properties. It involves the application of force, the displacement of our object, and something that tells us how much of that force caused the change in motion or was in the direction of motion. Now, this is a vector. This is a vector, which means they both have direction, but this is a scalar. So I want to be really clear. Work is done by forces that are in the direction of motion. I've said that 3 times. I don't want to repeat myself a lot more, but this is an excellent trick question for your tests. Only forces that are in the direction of motion can do work. Only forces that are in the direction of motion can do work. So mathematically, how this looks isn't much different than you would expect, but there's a special name for this kind of math. This is vector math. It's going to take 2 vectors and produce a scalar. Now, you haven't seen math like this before, and generally we don't write it like this very much. This is not a multiplication symbol. This is a type of vector product. There are 2 vector products in nature. There's the dot product and the cross product. This is the dot product. It produces a scalar as the result. And mathematically, what it says is how much of the force is in the direction of motion. That's what the dot product is about. Now, it's not complicated. To get rid of that dot product and turn it into a regular multiplication, you have to multiply by the cosine of an angle. But be careful. We use the same symbol for all angles in this class. I'm saying be careful because this isn't the angle of the ramp or necessarily the angle of a string, or you have to be very careful what this placeholder means. This is the angle between the force and the displacement. That's what that angle means. Remember how we used R for all sorts of things in our last unit, but they didn't always mean the same thing? Same idea here. This theta isn't necessarily going to be just the angle of the ramp, which you've come accustomed to. This is the angle between the force and the displacement. Now, I have a few other things I need to talk to you about before we get into the nitty-gritty here, but I want you to understand that this is a subset of what the real thing is. This is not what the real thing is. Just so you guys are aware, in real physics, work is an integral. And for you guys who are in pre-calculus or calculus, you understand that this means that there's something different actually happening. This definition of work allows us to deal with forces that are changing over the displacement. We have to make an assumption in this class, and that assumption is going to be that our forces are constant. You need to ask yourself that question first before you actually launch into using this. If the forces aren't constant, you can't use this. Which means generally if the forces aren't constant, you have to find another way to do your problem because there's no calculus in this class. So you need to check. You need to make sure we're dealing with a situation in which the force is constant. That will be something they will attempt to test. Do you understand the difference between that? So this circumstance is only when forces are constant. Otherwise, we have to take the changing force into account. That involves bigger math than we have. All right, here's where your calculator might come into use. We're just going to talk about how this is done in a very straightforward and simple manner. although I would expect you to be able to calculate the size of the frictional force on your own. I'm just giving it to you for this exercise, okay? So there's friction acting on the box. Coefficient of friction is 0.4. Friction is mu times the normal force, so 0.4 times 100 newtons is 40 newtons. There's a 40 Newton frictional force acting on the box to the left, and I'm pulling on the box with a 75 Newton force at an angle as seen in the picture. The box slides across the floor a total of 15 meters. Okay, I want to calculate the work done. Now, the box is experiencing 4 forces. Any one of them can be doing work. So what I want you to explore are all the different ways work can be done on the box. So think of it this way. There's going to be work perhaps by gravity, work by the normal force, work by the 75 Newton force, and work by friction. Lots of different ways work can be done on the box. We're going to test each one. Some of them might be doing work, some of them might not. But I want you to see how this process is done. You'll come to understand which forces are probably doing work and which ones aren't as you become more experienced. We're going to start with these. Now, just to get us started, quick sketch of the forces acting on the box. All right. Let's handle the easy one. Let's handle the work done by gravity. The box slides to the right. Gravity's acting downwards on the box. Work is the product of 3 things: the size of the force, the displacement of the box, and the cosine between the force and the displacement. So all 4 of these are going to have these 3 buckets that you have to think about: force, displacement, and angle. So gravity's easy. There's a 100 Newton force acting downwards. The box travels to the right 15 meters. Now here's where we have to do some evaluating. What's the angle between the downward force and the displacement to the right? Excuse me?
30.
I don't believe so. The box travels this way. That's the displacement. Force of gravity is this way. What's
90.
that angle?
90.
90, yeah. The box travels to the right, gravity's downwards, the angle's 90 degrees between them. Is the gravitational force doing any work? What's the cosine of 90? 0. Is the gravity causing the box to move to the right? No, so it did no work. Only forces that are in the direction of the displacement can do work. I'm not trying to trick you, I'm trying to show you how to do this. So the gravity didn't cause the box to move to the right, so the gravitational force can't be doing any work. We don't know what the normal force is. The 75 Newton force is pulling up a little bit. That's reducing the normal force. We could probably figure it out, but do we have to figure it out to answer the question how much work is done by the normal force? If you're seeing what I'm asking here, you should understand that you don't. Because the normal force is upwards, the displacement is still to the right. The angle between the normal force and the displacement is still 90 degrees. Now look, some of you guys don't know that, and you waited for me to write it in. Put something in your notes to tell you why you put 90 degrees there. Write yourself a little note right now that'll actually be helpful when you study, when I pop the quiz on you on Wednesday. Because you know that's going to happen. And on Wednesday, I don't want to be disappointed. We don't have much time for retakes now. It's the end of the year. All right, now we start getting into the stuff that's actually doing something. It should be clear to you, the 75 Newton force is causing the box to move. A portion of that force is in the direction of the displacement. That's where the work's going to be done. So the size of the force, 75 newtons. Displacement, still 15 meters. And now the angle between the displacement and the force. That's something that was given, and we can easily see it 30 degrees. Here's where you get lucky and finally get to use your calculator and figure something out. Peyton, did you do it? Can you tell me what you got?
974.28.
Say it one more time.
974.28.
974.28. Questions about that? Everybody else get that number? I'm hoping so. Units. We have newtons times meters. So the simple unit, or I'll say simple, but let's just say our base unit is newtons times meters. Just a quick aside, Newton meter is called a joule, and that is the unit of energy. I want you to be careful here. A Newton is a kilogram meter per second squared times m, which is meters, which means a joule is kilograms meter squared per second squared. That is a joule. It is a very complex unit. And you know that on the exam, they could probably play around with that. Kilograms per second squared, kilogram meters per second, kilogram meters per second squared, kilograms meter squared per second squared, and ask you which one of those is a joule. You see that, right? I'm sure of it. Joule is a small form of energy. It's even smaller than a calorie. There are 4.19 joules per calorie. That's a conversion fact, and I want you to have that conversion fact. You might need it. There are 4.19 joules per calorie. In food calorie terms, 4,190 joules in 1 big C calorie. So a joule is a very small form of energy. When we talk about units, joule is the least of them all. All right, back to our problem here. I'm going to go ahead and erase that Newton meters and write joule. Work done by friction. This one might be harder for you. I mean, I hope not, but it might be. The force is 40 newtons. The displacement is still 15 meters. But here's where you might have some trouble. I don't know. We'll see. What's the angle between friction and the displacement? Yes, sir? It is 180 degrees. Good job. The displacement's to the right. Friction is to the left. That's 180 degrees. If you don't know that or needed a refresher or you're still figuring that out, you should probably write yourself a note as to why that's 180 degrees. Write it right into your notes now. It is the angle between the displacement and the friction. The box is moving forwards, the friction's pointing backwards. Now, when you multiply 15 times 400, you get 600, right? Hope so. What's the cosine of 180? Positive work increases an object's energy. Negative work takes it away. Positive work increases an object's energy. Negative work takes it away. when you evaluate work being done on an object, at the end of the day, we will talk about the net work being done. The total amount of work by all the forces acting on the object. That is the net work being done. The total amount of work done by all the forces acting on the object. We can break it up like this. We can individually figure out the figure out the work done by each individual force, add them all together, and this would be the net work being done on the object. Right here, it looks like 374.28 joules of work, which means 374.28 joules of energy were transferred to the box. At the same time, some of that energy that was given to the box passed right through the box and ended up on the floor. As the box scraped across the floor, although we gave the box 974 joules of energy, the floor took away 600 of those joules, which is why the floor probably got warmer. Friction is what we call a non-conservative force, meaning once it takes that energy away, that energy's gone. Non-conservative forces take energy away, and generally, that energy is wasted. Now, this problem isn't too tough, but there's more to it than this. Is this part terrible? Okay, pretty straightforward. You understand you still have to be able to evaluate forces acting on an object. That doesn't go away. But there are some interesting things that you can do by knowing this information. But I need to press on because there's a little bit more that has to be kind of conveyed to you today. So kind of want to move this to the side for just a minute and emphasize this a bit. Net work. I said it's the work done by all the forces acting on the object. There's another way to say this. Net work is also the work done by the net force. Net work is also the work done by the net force. There's something very important about that. So I want you to get the words down. But net work is the work done by the net force. By definition, the net force is going to be in the direction of the acceleration. That's likely the direction of the displacement. Not always, but it's likely the direction of the displacement. I bring that up because if it is in the direction of the displacement, then we can drop the cosine of the angle. It's either going to be 0 or 180. Either that acceleration is speeding up the object or that acceleration is slowing down the object. If the acceleration is turning the object, then it's 90 degrees and no work is done. So I want to focus on the cases where the object is speeding up or slowing down. For just a minute. And the reason I want to do that is because we know that net force equals MA. I need you to follow this derivation. I don't need you to be able to do this derivation. Okay? I want you to follow this derivation, but I don't need you to be able to do this derivation, okay? You should have access to your motion equations. You may not, but you should have access to them. I mean, you should be able to flip right to them in your notes and find the list of 5 motion equations. If not, on your equation sheet, they're the first 3 equations on the equation sheet. There's one of them I want you to look for, because in one of them, there's the product of A times delta x. Can you find it? It's one of your motion equations. If you had them written the way I wrote them, then the one you're looking for looks like that. That's the one I want you to find. We're going to use it. We're going to substitute. I'm going to solve for A times delta X. And in this case, I'm going to regroup, pull the M out, and regroup A times delta X so that I can substitute. I'm going to distribute that M. Now, this derivation is important to me, but you don't have to know how we got to it. We just combined a motion equation with our definition for work. But it has an important and explicit result. This is called the work energy theorem. And it defines a new kind of energy. One you know about already because you had it in middle school, but this is where it comes from. This is known as kinetic energy. And it's the energy of motion. It is the most basic form of energy in the universe. All motion is a form of kinetic energy. And work directly changes an object's kinetic energy. So when net work is being done on an object, if it's positive, it's now going faster. And if it's negative, it's going slower. In the prior example you just had, the object had 378 joules of work done. If it started from rest, you should be able to tell me how fast it's going. And I don't mean that in a arbitrary way. I'm going to give you about 30 seconds to tell me how fast the object was going. An example with the box. 378 joules of energy was done to the box, 0.28, I think. Did I get that number right? 374 joules of energy were done to the box. If it started from rest, you should be able to tell me how fast it's going now. I'll give you a moment. I'm just going to pick on one of you to make sure we're all paying attention. Don't forget the mass of the box was 10 kilograms. Leo, how fast is the box going?
8.65 meters per second.
Sounds good to me. Somebody back him up? Sounds good. Now, there are some advantages here. One of them is if you use the work energy theorem, you shouldn't have to find the acceleration of the object. Energy is often about velocity and displacement, and energy problems are often about position and velocity. So let me just sum real quick what we've got so far. Our definition of work, it's a scalar measured in joules. Net work is the sum of all the work done by every force and can be written as the net force times the displacement times the cosine of the angle. The work energy theorem says that net work equals the change in kinetic energy, or 1/2 mv final squared minus 1/2
mv initial squared. This is what was introduced today. These are the three things I want you to walk away with for sure. We're going to press on, but this is a good summing spot. Okay? So I want you to try another one. Same box. $75 Newton force again. Pulls the box 15 meters up a ramp. The ramp is inclined 20 degrees. I'd like you to tell me how much work is done by the forces acting on the box. There are three different forces that act on the box. There's the normal force, there's weight, and there's a 75 Newton force. I'm going to leave friction out this time. To make this a little bit easier, we're going to say that the coefficient of friction is 0, so you can leave it out. I'd like you to find the work done by each of the three forces. Yes, sir?
How much is the box weight?
Let's say it's 10 kilograms again. Same box, just slightly different circumstance. Again, it's three different things. Force, displacement, cosine of the angle. All right, a quick walk around the classroom. Some of you see it, some of you don't. The first one's easy, 75 newtons, 15 meters, and it's a cosine of 0 degrees. The force is up the ramp, the box goes up the ramp, so they're in the same direction. That gives you 1125 joules. That one's not terrible. I don't know what the normal force is, but I don't think it matters. The normal force is going to be that way. And the box is going up the ramp. So the normal force and the displacement are at right angles to each other. So in this circumstance, the normal force doesn't do any work. It's not in the direction of motion. Now, there's a couple different ways you could have done the next problem. You could have found out how much of the weight was down the ramp, mg sine theta. But you don't have to. Work doesn't require that you break this up into components. The box has a weight of 100 newtons. That is the force of gravity acting on it. And the box goes 15 meters up the ramp. But now I need the angle between the displacement and the weight. The weight's downwards. This is the angle I need. It's not 20 degrees. It's 90 plus 20, 110. Now, when I work that out, I know the cosine of 110 is going to be negative. So in this case, gravity did negative work. I'm not surprised by that. I have to work against gravity to get the box to go up the ramp. So not all of the force I'm putting into the box is changing its velocity. Some of it's lifting it up. But I want to say that this gives us like 500 and something.
Yeah, 513.
So negative 513 joules. Total work done, 612 joules. The box started from rest, then that has to equal the change in kinetic energy, which means if the box started from rest, you could find out how fast the box is going at the top of the ramp. Yes, sir.
How'd you get negative 5?
I multiplied 100 times 15 times the cosine of 110. What do you get when you do that?
I got negative 1,498.
I think you made a mistake. 100 times 15 is 1,500. And the cosine of 110 is, I have negative 0.342. Is your calculator in degrees? We all right?
It's a radius.
That'll do it. That'll do it. Now, generally work problems aren't particularly hard. However, they can be tricky. I want you to understand, although there are some shortcuts coming up for what we can do using work, when it comes to straight out work problems, you're often doing a force problem and then something more. That's pretty typical. So, a brief reminder, if you use this formula, this kind of process, this can tell you how much the object's velocity changed under most circumstances without having to figure out the acceleration. Work problems are generally about position and velocity. We've done a lot of force problems, but work problems are generally about position and velocity. We're gonna start even cutting out the work part. I mean, we're gonna be looking more closely at energy over the rest of this week and less about work. But your homework's gonna have a mixture of work problems and energy problems. And some of it's some simple stuff. I want you to consider all of your exercise machines, any of the ones you've ever seen, generally have you lifting some weight. Have you noticed that? All the machines in the gym, you might push in some direction, but usually a weight's going up. There's a conversion there to tell you how much work you're doing. If you're on a treadmill, it tells you how much work you're doing, converts it into food calories. It uses that 4,190 joules to equal 1 big C calorie to tell you on the screen how many calories you've actually burned. All of that stuff that is in any gymnasium is all based on the simple rules for work. I want you to think about this for just a moment. Some of you look like you work out. Some of you look like you should work out. Let's go back to that 10 kilogram box. It's not heavy. 10 kilograms is just a little under 25 pounds. Thinking most of you could probably lift it. Most, I'm afraid. And let's say your job is just to lift it over your head. That's 2 meters. This is your exercise for the day. How much work is done lifting the box 2 meters? It's an easy question. Work it out. How much work do you do lifting the box 2 meters? I would assume you apply an upwards normal force to the box. Let's assume that the force you apply is just enough to lift the box, which is 100 newtons. I'm saying that because if you lift it 2 meters, the work done would be 100 newtons times 2 meters times the cosine of 0 degrees, or 200 joules. Let's say you eat 1 candy bar. A candy bar is 200 food calories, which means a candy bar is, let me see if I did this right, 838,000 joules of energy. How many times would you have to lift that box to get rid of that candy bar?